Hi, I'm going to tell you about how jets are born and how they die. I'm going to try and understand what is the optimal jet diet, what sets their power, collimation, acceleration, mass loading, and emission. And if it happens that the black hole and accretion disk midplanes are misaligned, what happens to the jets? Do the jets still exist, or do they disrupt? And which way, if they exist, do they point? Do they point perpendicular to the disk midplane or the black hole midplane? Finally, what happens when the jets fall apart? What causes them to do so? Let us take a look at an example of the M87 jet, which extends out for about 5 kiloparsecs before falling apart. What's remarkable is that it reaches relativistic velocities, Lorentz factors of about 6, and also it manages to maintain almost a single power law dependence of jet cross-section versus distance. Z goes as r to the 1.7 power, over 5 orders of magnitude plus a little bit. How do jets manage to do that? I will be classifying the jets on this two-dimensional playground. The vertical axis is the thickness of the accretion disk. Thicker disks are there, thinner disks are over here. And the horizontal axis is the strength of the vertical magnetic field. If there is a lot of magnetic field, it will be easier to make jets. If there is none, we expect the jets won't be there because it is the vertical magnetic field that the black hole needs in order to produce the jets. So let's focus on the easiest case of thick disks with vertical magnetic fields. In this case, as you can see, the jets form just fine, but what's really challenging is to resolve the scale separation between the tiny little black hole and the large galaxy. As you can see in this simulation, the scale separation is pretty good, but actually it's just 3 orders of magnitude. What we really need is to produce the jets by black holes that span more than 5 orders of magnitude in space and time, and this is precisely what postdoc Kaushik Chatterjee has done, and remarkably has obtained very good agreement between the shape of the jet, the parabolic shape that extends for over 5 orders of magnitude in distance, and also the Lorentz factor that is measured in the M87 jet. What's also really cool is that if we look at the jet interaction with the ambient medium and zoom in on it, we will find that the wind through which the jet is propagating is mixing its heavy gas into the light jet. And these interface instabilities are naturally mass loading the jets and perhaps determining their velocity that we observe at large distances, which could be really important for making them shine. We've learned that if we give black hole large-scale vertical magnetic flux, it will happily produce the jets. Well, that's perhaps not surprising. So let's see other cases when black holes don't produce jets, because actually 90% of them don't. So let us try and move over here. We're still going to consider a thick disk, but we will not give it any vertical magnetic field. We will consider purely azimuthal magnetic field as the initial condition, in which case we do not expect the system to produce any jets, because vertical field is what's necessary for jet formation. Here you see vertical slides through our initial conditions. A donut of gas on an orbit around a rapidly spinning black hole. The dimensional spin is 0.99, 99% of the maximum possible spin, which would be unity. We have 0 vertical magnetic flux. All the magnetic flux is purely azimuthal, and the thickness of the disk is about 1/3. It's a pretty thickish accretion disk. The left panel shows the zoom on the right panel, on the central regions of the right panel. The right panel is about 1,000 gravitational radii of the black hole on the side, and the left panel is 100 gravitational radii of the black hole on the side. So let's run the simulation and see what happens. As you see, almost immediately, there are these black lines that appear. These are magnetic field loops of the poloidal field, the vertical field that we didn't have at all At the beginning, these vertical magnetic field lines are produced by the turbulence self-consistently through alpha-omega dynamo that takes toroidal field and converts it into vertical field. The jet power becomes comparable to the accretion power. So that in fact, although we started with almost no vertical magnetic flux, actually zero vertical magnetic flux, we ended up with the case when the vertical magnetic flux was in equilibrium with the accretion flow, and the jets that the flux produced are comparable in power to the accretion power, which means that our accretion disk approaches the magnetically arrested disk state, which produces the jets that are as strong as possible. It's spectacular that jets are so resilient. Even in this case, the jets manage to save themselves. What if we tilt this whole system? What if the tilt is the component that kills the jets? Well, let's try and check this out. As before, we'll start with the top right, the easiest case. Thickest disk, vertical field, but tilted. And in this case, the theory tells us that the accretion disk that's tilted will be subject to the black hole frame dragging forces due to the rotation of the black hole, so that a disk will feel that the space is dragged around, and so the disk will precess as a whole, just like you can see over here. However, that is only expected to be the case for a geometrically thick disk. If we consider a thin disk, then in this case we expect the inner parts of the disk to align with the equatorial plane of the black hole by the prediction of Barton and Peterson of 1975, more than 45 years ago. This, however, effect has only been seen in pseudo-Newtonian simulations. So once the full effects of general relativity in magnetic fields are included, this has never been seen. So does it mean that this effect doesn't exist in general relativity? Or perhaps it does, we just haven't seen it. And it is a really challenging problem. That's because the cost to simulate such a thin disk simulation scales as h over r, the aspect ratio of the disk to the -5th power. So if you want to consider this that is twice as thin, we will have to run the simulation for 32 times longer. Obviously that's not realistic. So how can one possibly pull this feat off? We developed a new tool that is able to run on graphics cards, which are much more powerful than the central processing units of the supercomputers. And we have added, or rather Matthew Lishka has added extra bells and whistles to this code. This code is now capable not only of adaptive mesh refinement in space, but also in time, which gives us a really large speedup. A combination of all these features allows us to operate on the equivalence of billion CPU hours a year, which is precisely what enables the type of research that you're about to see. So let us take a look at a pretty thick accretion disk with aspect ratio of about 0.1, tilted by 45 degrees relative to the black hole midplane, and the black hole is spinning at 93% of the maximum spin. The disk you can see in blue, and the jets you can see in red. So as expected in this case of a thickish disk, the accretion disk is undergoing precession around the black hole, and the jets, which is spectacular, are not only happily produced, but they also are going around together with the disk and precessing as well, which means that by looking at the jets at large distances, it is possible to infer the behavior of the accretion flow at really small radii where strong field gravity dominates. Tilted disks with vertical magnetic fields produce powerful jets. What is left for us to explore? Perhaps we could take a look at a thin disk with a lot of vertical magnetic flux. As before, on the left, you've seen a window of about 30 times 30 gravitational radii on the side into accretion disk, which is a zoom in on the central parts of this right panel, which is about 150 times 150 gravitational radii on the side. So let us run the simulation and see what happens. We're looking here for two things. First, we're looking out for jet formation, and the other thing is for the alignment of the accretion disk. Wait, the accretion disk has just aligned. This is the first demonstration of Barton-Peterson alignment in the presence of general relativity and turbulent magnetic fields. So what we see, we can kill two birds with one stone. If the disk is thin enough, it can not only Barton-Peterson align, it can also produce powerful jets. So, jets are still there. What if we tilt the disk even more? What if we tilt the disk by 65 degrees instead of 45 degrees? And you see something interesting is going on over here. If we look in 3D, we see that the inner part of the accretion disk has torn itself off of the outer part of the accretion disk. So what we think happens here is the black hole causes the inner accretion disk to precess due to the frame dragging torques that force the inner disk to precess as a whole. But the outer disk is not really happy, it doesn't want to precess. If the accretion disk is not strongly enough connected in order to transport this precessional torque, then the disk will tear apart and the inner disk will precess on its own, which is precisely what we're going to see in this movie, which starts with a flat accretion disk that's tilted by 65 degrees. You see the inner disk tears off of the outer disk and takes the jets with it. Then these jets slam into the outer disk and completely destroy it, which is spectacular and should lead to fantastic fireworks on the sky, which are yet to be explored theoretically. And as you can see, the disk is at it. It continues tearing up into smaller and smaller Matryoshka doll-like structures, and you can see that we're left with several independently precessing accretion disks. When we are looking at tilted thin disks with vertical magnetic fields, not only do we get jets, we also get a plethora of really exciting phenomena such as disk alignment and disk tearing. So what happens if we consider the only remaining option here for suppressing the jets? Perhaps if we don't give it any vertical magnetic flux and consider thin tilted disks, then the jets will go away. This is perhaps the most expensive general relativistic magnetohydrodynamic simulation ever. It has been performed at the largest national supercomputer summit, and it uses resolutions which are about a factor of 10 larger in each dimension. Around 14,000 times 5,000 times 8,000 cells. This is the resolution in the accretion disk where the adaptive meshes focus all of the computational power. The left side here is showing a 3D view of the accretion disk, which starts out as a flat pancake, and then over time it will be warped by the forces of the frame dragging of the black hole. The right panel shows the vertical slice. The disk is tilted initially by 70 degrees, and it's the thinnest disk simulated ever. What's really crucial here is that the magnetic field is purely azimuthal. This is the first simulation of a tilted thin disk with a purely azimuthal magnetic field. So let's run the simulation and see what happens. Well, we can clearly see that the forces of the frame dragging cause the inner disk to warp. And not only that, but it also causes the inner parts of the disk to tear off periodically from the outer disk. So this tearing of the inner parts of the disk of the outer disk is really interesting, because if the inner disk produces a lot of emission, we will see quasi-periodic oscillations perhaps that has been puzzling us for a long time. It's a long shot, of course. We're going to have to try and investigate this in more detail. But what's really interesting is that even in the absence of poloidal magnetic flux, we've seen the effect of disk tearing. And not only of the disk tearing, but we also seen the effect of the alignment of the inner disk with the black hole, which is about to happen right now. This means that Barton-Peterson effect and disk tearing are not artifacts of strong vertical magnetic fields. Here there is no large-scale poloidal magnetic field. There is no jet. For the first time, we finally don't see any jet, although we start with large-scale magnetic flux in the azimuthal direction here. So we're not seeing the formation of large-scale magnetic flux in the context of thin disks. Why that is so, why thin disks so different than thick disks is a question for the future. So what happens when the jets that were produced by the black hole slam into the ambient medium? Here are two of my most favorite jets, the Cygnus A jet and the M87 jets. And you can see that they are very different. In the case of Cygnus A, the jets extend out to almost 100 kiloparsec away from the black hole, whereas in the case of M87, you can see that the jets fall apart well within the galaxy at just about 5 kiloparsecs away from the center. So what causes the jets to fall apart? What is the physics that is underlying this puzzle of Van-Frilly dichotomy of jets, which has been mesmerizing the community for the past 46 years? Could this be a magnetic instability of these magnetic springs, which are the jets? And this is precisely what we set out to check. So here are the two simulations, each of which is meant to mimic either the Cygnus A-like or the M87-like jet. You can see this is Cygnus A and this is M87-like jet. At the center, there is a rapidly spinning magnet which is going to launch jets sideways. And we will first focus on the more powerful jet over here. So what I do here is I trace out one field line with magnetic field line shown with white and with the gas on top of it shown in blue. And you can see that the jet really behaves like a magnetic spring, or perhaps you can make an analogy that behaves like a bendable drill. So the drill is wobbling left and right, but it's keeping itself together. It's not getting disrupted. Although the tip of the drill gets continuously reprocessed into the strong backflows, something that you can see over here, strong backflows in this example of a strong, powerful Van-Frilly type 2 jet in Cygnus A. You can also see large-scale bands of these jets, similar to what you can notice in the Cygnus A jet and other Van-Frilly type 2 jets. Here, though, in the less powerful jet, the only difference between these two simulations, by the way, is the jet power. This one has a jet that is 100 times less powerful than the top one. You can see that this jet is still struggling to make itself out. You can also notice that the jet ties itself into knots and gets stalled well within the galaxy. This circle shows the distance of 10 kiloparsec. So what's happening here, we think, is the activation of the magnetic kink instability. It's analogous to taking a spring and squeezing it vertically, so it kinks sideways. And this is what we think precisely is going on here. It's a magnetic, three-dimensional magnetic kink instability. We can also extend the simulations to include the accretion flow around the black hole, and this is precisely what has been done by Kaushik Chatterjee, whose work you already saw at the beginning of this talk. And you can see that the accretion disk, which is shown in red here, forms these two beautiful dark jets that kink and fall apart and inflate these beautiful bubbles, similar to what the observations are telling us. So how do the jets shine once they slam into the ambient medium? It turns out that if we zoom in onto the region where the jet first encounters the ambient medium, which would be HST1 or so, in the case of M87, we see that the jet develops wiggles inside of itself. In fact, we think that there is a lot of dissipation associated with these wiggles. We observe that in the simulation, and you can see here the formation of this internal kink instability where the jet twists onto itself and dissipates magnetic energy, hits itself up, and accelerates non-thermal particles. This process can be responsible for the production of flares and powering the emission of these features in the jet, such as HST1 in the M87 context. So let us sum up. The jets are really resilient. If you give a jet, if you give a black hole a large-scale magnetic field, either a vertical magnetic field or horizontal azimuthal magnetic field, it will produce a jet. The only exception we have been able to find is really thin, geometrically thin disks that are not able to produce jets. We are beginning to understand through the simulations the acceleration, dissipation, mass loading, and the physics of disruption of the jets. We are also now beginning to explore the typical tilted accretion systems, where the midplane of the infalling gas is tilted relative to the midplane of the black hole. And finally, these systems show a plethora of really exciting new physical effects, such as disk tearing, Barton-Peterson alignment, and jets that are destroying accretion disks. Thank you so much for your attention. I'm looking forward to your questions.